Welcome to Principles of Ecology. Today, we are diving into two of the most powerful physical forces shaping life on Earth: temperature and light. Imagine stepping outside on a freezing winter morning without a coat. You shiver, you feel sluggish, and you immediately seek warmth. Plants and animals face this exact struggle every day, but they cannot simply walk indoors. In this lecture, we will explore how these invisible boundaries dictate where organisms can live, how fast they grow, and how ecosystems function from the ground up. Let us begin our journey. Now that we understand the premise, let us look at why temperature is considered a master ecological factor. At its core, temperature is simply a measure of ambient thermal energy. But at a biological level, it is everything. It governs the kinetic energy of molecules inside every living cell. This kinetic energy determines the rate of enzymatic reactions that drive an organism's metabolism. If the temperature drops too low, enzymes become inactive, and ice crystals can actually rupture cells. If it gets too high, vital proteins denature, and the organism dies. Temperature directly controls the speed of life. Building on how temperature affects cells, this brings us to the concept of tolerance. Every species has a specific range of temperatures within which it can survive, known as its range of tolerance. Within this range lies an even narrower optimum zone, where the organism thrives, grows, and reproduces most efficiently. This concept is absolutely crucial because it explains the global distribution of life. It is the reason we find polar bears in the Arctic and camels in the Sahara, but never the reverse. These thermal limits create the world's major biomes, from tropical rainforests to freezing tundras. To visualize what we just discussed, let us look at the ecological tolerance curve. On the horizontal axis, we have temperature, ranging from cold on the left to hot on the right. On the vertical axis, we measure population size, or performance. Notice the large peak in the center. This is the optimum zone, where the population thrives. As we move away from the center into the zones of physiological stress, the population drops. Finally, at the extreme ends, we hit the zones of intolerance, where no individuals can survive. This curve perfectly maps an organism's thermal boundaries. Now that we have seen how temperature limits life, let us quantify its effect on metabolism using the temperature coefficient, denoted as Q10. This formula calculates how much a biological process, like respiration, multiplies when the temperature increases by exactly 10 degrees Celsius. In the equation, R1 is the initial metabolic rate at the lower temperature, T1, and R2 is the rate at the higher temperature, T2. If Q10 is exactly 2, it means the metabolic rate doubles for every 10-degree increase. This gives ecologists a precise mathematical way to predict responses to heat waves. Before we move on, let us see this formula in action. Imagine studying a frog's oxygen consumption. At an initial temperature of 15 degrees Celsius, the rate is 4 units per hour. You raise the temperature to 25 degrees, and the rate increases to 12 units. We need to calculate Q10. We plug our values into the formula. The temperature difference in the exponent's denominator is 25 minus 15, which is 10. 10 divided by 10 simplifies the exponent to 1. The base is the ratio of rates, 12 divided by 4, which is 3. 3 to the power of 1 is 3. Physically, this means the frog's metabolic rate triples for every 10-degree increase, explaining why it is highly active when warm. Having explored temperature, We now turn to the second master factor, light. Think of plants as the ultimate solar panels of an ecosystem. Light is the raw energy that powers almost all life on Earth. Without it, plants cannot grow, herbivores have nothing to eat, and predators starve. But not all sunlight is useful. Plants rely on a narrow band called photosynthetically active radiation, ranging from 400 to 700 nanometers. Beyond energy, light is a critical signal. The daily duration of light, or photoperiod, tells organisms what season it is, triggering vital behaviors like migration and flowering. Building on the idea of light as fuel, let us look at how it structures entire habitats. Light forms the absolute base of the ecological food web through photosynthesis. In aquatic ecosystems, light availability dictates how deep plants and algae can survive, creating distinct vertical zones of life. In terrestrial forests, tall trees compete fiercely for sunlight, forming a layered canopy. This canopy dictates the microclimate for all the plants living on the dark forest floor below. If light is blocked by muddy water or dense leaves, the productivity of the entire ecosystem drops dramatically. Since light decreases as it travels through environments like water or forest canopies, ecologists use the Beer-Lambert law to calculate exactly how much light reaches a specific depth. In this equation, I sub z is the light intensity at depth z. I sub 0 is the initial light intensity at the surface. The constant E is the base of the natural logarithm. The variable k is the light extinction coefficient, which measures how murky the water or dense the canopy is. Conceptually, this formula shows that light intensity decays exponentially as you move deeper. If the water gets muddier, k increases, and light drops off much faster. Now that we have the mathematical model, let us apply the Beer-Lambert law. Suppose you are studying a clear lake. The surface sunlight intensity is 1,000 units. The water's light extinction coefficient is 0.5 per meter. We want to find the light reaching a depth of 2 meters to see if algae can survive. We substitute our values into the equation. First, we multiply the coefficient, 0.5, by the depth, 2, giving us 1. Our exponent becomes -1. The expression e to the power of -1 is roughly 0.368. Multiplying this by the surface intensity of 1,000 gives us 368 units. This means only about 37% of light reaches this depth. To fully grasp the result we just calculated, let us look at the light attenuation graph. On the horizontal axis, we have light intensity, starting at I sub 0 at the surface. The vertical axis represents depth, increasing as we move downward. Notice the shape of the curve. It is not a straight line. It is an exponential decay curve. As depth increases, the light intensity drops off very rapidly at first, and then levels out as it approaches 0. This visual perfectly captures the Beer-Lambert law, showing exactly why deep aquatic environments are completely dark and devoid of photosynthetic life. We have covered a tremendous amount of ground today. Let us review the most important ideas. First, temperature is a master factor that dictates the pace of life by controlling enzyme kinetics, which we can quantify using the Q10 coefficient. Second, light is the fundamental energy source for ecosystems, with plants relying on the specific PAR spectrum to drive photosynthesis. Finally, light availability decreases exponentially through mediums like water, a phenomenon perfectly described by the Beer-Lambert law.
Understanding these two physical factors allows us to predict where species can survive and how entire ecosystems are structured. Excellent work today.